Hello everyone, myself Riya Bajaj and today I am going to present a seminar on crystal field theory. These are the contents of my seminar. The points to be covered are introduction, limitations of VBT and need for CFT, assumptions of CFT, the types of d orbitals, crystal field splitting in octahedral and tetrahedral complexes, concept of CFSC, calculation of CFSC, conclusion and references. So, let's get started. So, crystal field theory was first developed by two physicists, Bethe and Van Vleck, in 1932. This theory is applied to ionic crystals and therefore known as crystal field theory, but later on it was applied to coordination compounds or the complexes. CFT provides an electrostatic or ionic approach towards ligand metal ion interactions. We all are well aware of the fact that development of every theory is a consequence of drawback or demerits in the previously developed theories. Before CFT, VBT was applied to the coordination compounds or complexes. Although VBT, that is valence bond theory, has explained various aspects of bonding in metal and ligands, that is formation of complexes, it has failed to explain certain parameters also. So let us see what are the limitations of VBT and why there is need for CFT. So VBT has failed to explain the electronic spectra, which is the most important property possessed by the complexes. Secondly, it has failed to explain the magnetic moment of most of the complexes. So a more radical approach was put forward which had only room for electrostatic forces, and this approach is provided by CFT. So let us see what are the assumptions or the postulates of crystal field theory. First of all, the theory considers interaction of d orbital of metal ion with the approaching ligands. The metal ion and ligand interaction is purely electrostatic. Now we know that in electrostatic or ionic bond, two types of ions are present, the positively charged cation and the negatively charged anion. So in case of coordination compound, that is complex, we are going to consider central metal ion as positive cation and the ligand as negatively charged anion. We know that ligands can be either negatively charged or neutral. So we are going to consider the negative ligand as point charges, for example Cl negative, Br negative, Cn negative and etc. And the neutral ligand as point dipoles, for example NH3, H2O, etc. Next, the d orbitals of free metal ion are degenerate, that is, they are having same energy. But on the approach of ligands, due to repulsion between the electrons of ligand and the electrons of central metal ion, that is, the inner electrons, the degeneracy of d orbitals get destroyed and they get splitted into two different groups depending upon the geometry and somewhat on the nature of ligand also. Lastly, this theory does not consider the covalent nature of metal ligand bonds. So, let us proceed towards the concept of crystal field splitting. But before that, we should know what are the types of d orbitals. The d orbitals are categorized into two different types depending upon their geometry and their arrangement in the three-dimensional space. First one, the non-axial ones, these are dxy lying between x and y axis, dyz lying in between y and z axis, and the dxz lying between x and z axis. The axial ones, these are dx square y square, their lobes lie on x and y axis, and the dz square, its lobes lie on the z axis. A 3D weave of d orbitals interacting with the ligand is shown here. Now let us see the concept of crystal field splitting. Crystal field splitting refers to the difference in energy of d orbitals of metal ions splitted due to approach of ligands. It is denoted by delta. Crystal field splitting explains the difference in color of complexes of same metal ion with different ligands. Also, it explains the difference in observed and theoretical values of magnetic moment. The diagram shown below explains the crystal field splitting. On the left hand side, the interacting metal and ligand. Due to this, the splitting of d orbitals occurs as shown here. In our consideration, we are going to study two types of geometries, octahedral and tetrahedral. So let us see the crystal field splitting in octahedral geometry. In case of octahedral geometry, the approach of ligand towards central metal ion occurs along the axis. Due to this, The axial orbitals are affected the most and they attain a high energy state, whereas the non-axial ones occupy the low energy state, and the splitting occurs as shown here. The T2G set or level, which is for the non-axial ones, which is triply degenerate having lower energy, and the EG, that is axial orbitals, that are double degenerate having higher energy. The difference in between energies of T2G and EG is denoted by delta O or 10 dq, which is known as crystal field splitting energy. Let us consider crystal field splitting more diagrammatically. On the left hand side, you can see d orbitals in free metal ion. These are degenerate. Due to approach of ligand, they attain a hypothetical high energy state and immediately get splitted into two energy levels, Eg having energy plus 0.6 delta and T2G having minus 0.4 delta. And the difference in between these two energy levels is nothing but crystal field splitting energy. Now let us consider the crystal field splitting in tetrahedral geometry. In case of tetrahedral geometry, inverse to that of octahedral occurs. The approach of ligand towards central metal ion occurs in between the axes, which causes splitting of d orbitals in such a way that the non-axial orbitals occupy high energy state, that is T2G set, which is triply degenerate, and the axial orbitals occupy lower energy state, that is EG set, which is double degenerate. And the difference between energy of T2G and EG is denoted by delta T or 10 dq, which is nothing but crystal field splitting energy. Let us see the crystal field splitting in tetrahedral geometry through a short video representation. Here, the splitting occurs in such a way that T2G having higher energy and EG having lower energy. The diagram shown here explains the crystal field splitting in tetrahedral geometry. On the left hand side, you can see the d orbitals in free metal ion. They are degenerate. Due to approach of ligand, they occupy a hypothetical high energy state and gets immediately splitted into two different energy levels, T2 having energy plus 0.4 delta T and E having minus 0.6 delta T. And the difference between these two energy levels is known as crystal field splitting energy. We all are well aware of the fact that when a molecule is in high energy state, it becomes unstable. Due to crystal field splitting, the complex must have been unstable, but this does not happen because an energy equivalent to crystal field splitting energy stabilizes the molecule, and this energy is known as crystal field stabilization energy. So let's proceed towards the concept of CFSC. The additional energy which is responsible for stabilization of complex due to crystal field splitting is known as crystal field stabilization energy. Because this energy stabilizes the molecule, its magnitude is same as that of crystal field splitting energy. It is denoted by delta O 10 dq for octahedral and delta T or 10 dq for tetrahedral geometry. A diagram shown below explains the difference in the energy of splitting in octahedral versus tetrahedral geometry. Now let us see how can we calculate crystal field stabilization energy. For octahedral complexes, CFSC is given by the formula shown here, that is minus 0.4 Nt2G plus 0.6 Neg into delta O plus Mp, where delta O represents the crystal field splitting energy and Mp represents the pairing energy that is required for the pairing of electrons, or minus 4 Nt2G plus 6 Neg in the form of dq plus Mp, where Nt2G and Neg represents the number of electrons in T2G and Eg orbitals respectively. Similarly, for tetrahedral complexes, CFSC is given by the formula shown here, that is minus 0.6 Neg plus 0.4 T2G delta T plus Mp, where Nt2G and Neg represents the number of electrons in T2G and Eg orbitals respectively. So from this we can conclude that CFSC 0 when T2G and Eg are symmetrically filled, that is for D0, D5 and D10 configuration, it is completely calculated values. From the CFSC values, it is observed that in octahedral complexes, every electron enters in T2G orbital stabilizes the complex by 0.4 delta O, and each electron entering in Eg orbital destabilizes the complex by 0.6 delta O. And in inverse to that, in tetrahedral complexes, every electron entering in T2G orbital destabilizes the complex by 0.4 delta T, and each electron entering in Eg orbital stabilizes the complex by 0.6 delta T. So in this way we can say that CFT has provided us a more logical and mathematical approach towards metal ligand interaction, formation of stable complexes, their electronic spectra, color, and magnetic properties. These are the references I have preferred for the preparation of seminar. You can check them out. They are having some amazing concepts of inorganic chemistry. Thanks for watching.